Hi, thanks everyone. So I don't know if you've downloaded the materials yet, but if you want to follow along and do the exercises, you should go to this address. Is that visible at the back? Yes? Okay, great. So github.com/jni/SciPy Japan 2019, and you can either git clone that or you can just download here. So can people raise their hand if they have used Jupyter Notebook before? Okay, most people, but not everyone. So I will give a brief introduction to that. So once you download it, how many people have used the terminal before? Not everyone. Okay. So to launch Jupyter Notebook, you need to launch a terminal. On Windows, it might be a bit different from here. Let me clear this. So this is the repository that I just downloaded. And to start a Jupyter Notebook, you type Jupyter Notebook. So this starts a server that listens for Python commands and gives you back Python results. And it opens a web page. And that's how you interact with Python in this case. So if you click on the notebook, Advanced NumPy Patterns, it will open a bunch of text and code intermingled, and that's how we're going to do the tutorial today. Before we go any further, I'm going to say this is a tutorial that I have given at a course called Advanced Scientific Programming in Python. And in that course, we always use pair programming. So everyone works in pairs rather than individuals. And we find this really beneficial because you can discuss as you work problems together. So I see not everyone is paired up. I would encourage you to move around and find a partner so that you can work together on the problems. The next logistical issue is there are helpers in the back of the room. So if you have any questions at any point, raise your hand and they'll come around. Okay. Any questions so far? No? The other thing, if you want me to stop, slow down, please raise your hand. This is supposed to be an interactive tutorial. And yeah, we'll stop for questions. Everyone should participate. So I'll talk a bit about myself. I was a biologist once upon a time, and I started using Python to do my research, analyze my data, and little by little I started contributing to the packages in Python that I was using, and now I'm fully involved in just software development for scientific Python open source projects, in particular a project called scikit-image for image analysis. And I'm at Monash University in Melbourne, Australia. So if you want to talk about bioimage analysis, talk to me at the break or during the conference. The other thing that I'll say about me is I also wrote this book, Elegant SciPy, which is about using the SciPy library. And there will be a book signing at the end of the day at the job fair. The book itself has been translated to Japanese as well. The original book in English is available open source on the web. I don't think that's true of the Japanese one. So if you want the Japanese one, get a copy. Okay. Any questions about that? Yes. Can you make the font bigger? Yes, I can. Thank you. Okay. Great. Can you speak a little slow? Okay. I can try. Let me see if I can get rid of the header. Okay, so that gives us a bit more room. Okay. How many people in the room know a bit about biology? couple of people. Okay, so this example. Sorry, so my examples are mostly from biology because that's my expertise. So I'll try to explain the biology behind this. So I'm going to go straight to the board and talk about what this table means here. Okay, so you might know that every single cell in your body has DNA, and the DNA in every cell is the same. So that is what's called your genome, and all of them are the same, even though you have cells that are very different. You have nerve cells, skin cells, gut cells. So the difference is that if you have this DNA inside of your cell, the DNA is divided into things called genes, and that produces a thing called, this is DNA, that produces a thing called RNA, which is a single strand, not a double strand. And this is called gene expression. And so different genes have different lengths, and they get produced at different levels. So the quantity of this RNA is different in different cells, and that is why you have different types of cells. They have different levels of this RNA. And then this later goes into proteins, but we're not going to talk about that. Any questions about how that works? Okay. So in order to understand things about cells and disease, we often want to measure this in different cells. So for example, you might want to measure this in a healthy skin tissue versus a skin cancer cell, and try to understand why the cell is cancerous. To do that, these are small molecules. You can't just look at the measurement. We have this thing called RNA-seq. And the way RNA-seq works is that this RNA gets amplified many times. This is all using chemical reactions. And this one also gets amplified many times. You try to keep this proportional, so the amplification of this thing will be the same as this thing, so that when you measure the amount here, it will be proportional to the original amount. And then what happens after this is that this gets cut up into little pieces, let's say 100, it's called nucleotides, that's the unit of DNA. And then using machines, you can get this sequence, and then because we know the whole genome, you can figure out that this sequence came from this gene, and then the number of sequences that you get from this gene gives you the expression level. Okay, so that's the crash course into gene expression, and that's the kind of data we're going to look at. Two things that I want to point out. You can see that this gene is longer than this gene. So that means that the count of, these are called reads, that you get for this gene will be proportionally bigger. But what we are actually interested in is the number of these molecules. And so we want to normalize the data by the length of the gene. The other thing is that if you take two samples, one of the healthy tissue, one of the cancer tissue, or cancer tissue from different patients, this amplification will be proportional within one sample, but it will not necessarily be proportional between two different samples. And so you also have to divide by the total number of reads that you get. So that's what we're going to be using NumPy to do. Okay. I'll leave this here. Any questions about gene expression? Okay, great. So So now we have here a very small toy example. We have 3 genes and 4 different cell types, and these are the number of reads that we get for each gene. So if you do this using pure Python lists, then this is what it would look like, for example. Now if you do expression data, you get 3 rows of data. By the way, I mentioned that I would introduce Jupyter Notebooks. So Jupyter Notebooks have 2 things there. They have text cells. They're called markdown cells. And you can change these. So you change these by clicking on them. And then to execute them, you press Shift-Enter. And that executes and then goes to the next cell. This is the same for code. You can click on them to edit them, and then you can press Shift-Enter to execute. There is also, if you prefer to use your mouse, toggle toolbar, you can press Run, and it runs that cell. Okay? Let's get rid of that again. Okay. So do people have any suggestions for why you would not want to use pure Python lists to work with this data? Okay, so I'll tell you the main reason. The main reason is the way Python list works. This is not a list of integers, but it is in fact a list of pointers to integers. So if I have my list of values here, what I'm actually getting is a pointer to a Python object, which contains the number 100, and it contains something called a reference count, and other data related to the Python object. And you will have another one for here. For 0, and another one for 200. Okay, so this is actually a very inefficient way to store this data, because you have a bunch of extra stuff for every number that you have. And the other thing is that in modern computers, when you grab something from RAM, you don't just get the thing that you grabbed, you also get other values. So if I grab this thing, if I say give me the value at this point, it will come with this, and then basically around 8 kilobytes of data around that. So when you do a NumPy array, you actually have a single object with the numbers all next to each other, and then that one object has a ref count and some other metadata associated with it. So NumPy arrays, from a storage perspective, are much more efficient, and also when you are doing computation, it's more efficient, because when you grab this number to process it in your processor, you also get the next few numbers, and typically in a NumPy array, you will actually be using those numbers to do your computation one after the other. Okay, so with NumPy, one of the ways that you can create a NumPy array is by taking this kind of nested list and just calling np.array on that. Okay, so now we have a NumPy array containing our data. So I mentioned with the gene expression that we wanted to divide by the gene length, and we also wanted to divide by the total library size, the total number of reads, because that will get rid of the amplification factor that you get in different samples. Okay, so the normalized version of this table is called RPKM, which stands for reads per kilobase. Another word for nucleotide is a base. So it's reads per kilobase per million reads. So that's the two divisions, per kilobase per million reads. Okay, so I'm going to talk about what a NumPy array is internally, because that will help us to do some pretty fancy things with them. So these are a lot of attributes. I think most people who have used NumPy know that a NumPy array has a shape and a d-type, but there are other things that are also useful, which is the size, which is the total number of elements, and ndim, which is the total number of dimensions of the array. So in this case, for example, you have a two-dimensional array because you have the rows axis and the columns axis, but you can have 3D or 4D or higher arrays. And a.strides is something that I'll talk about in a bit. Okay. So if you run that cell, you get this. So the array that we created before has 12 elements, 2 dimensions, and has a shape of 3 rows and 4 columns. It has an int64 data type, so these are 64-bit integers. And strides, this is how many steps you need to take to get to the next element on that axis, and these are measured in bytes. So I will, let me explain a bit how that works. Okay, so we said that our array has 3 rows and 4 columns, but actually your computer memory doesn't have any concept of rows and columns. You can think of your RAM as one long street with numbers along that street, so everything is a linear position along that array. So the way that NumPy arrays get around this is by having this thing called strides. So we saw that the strides were 32, and this means that you need to do 32 bytes to get to the next element in memory. So actually, this is how the data is stored in your RAM. There's 12 positions. That's actually pretty good. And they're stored in what's called, by default, they're stored in what's called row major order. So they're stored in this one, then this one, then this one, then this one, and then you get to the next row and you do this. So this is the way that the array is ordered in your computer memory. And in order to get to the next element along a row, so to go from here to the next element, you have to jump 32 bytes. In order to jump to the next element along a column, you have to go 8 bytes, and this is because these are 64-bit integers. Okay? Any questions about that? Okay. Okay, so that's strides. I mentioned that the ordering is called C-contiguous. You can also have F for Fortran order contiguous, and that would mean that you would go along the rows first. And that's just the ordering of the array in memory. Okay, and there is another attribute called a.data, and that just points to the start of that array in memory. So you can do things in NumPy arrays like view those bytes in memory in a different way. So here I'm going to take that array, I'm going to ravel it, which means make it linear. So actually, let me explain what Ravel does. A.Ravel. So Ravel takes my 3x4 array and it gives me the 12-element array that is underlying the data. And any number of dimensions that you have, it'll just turn it into a single linear set of data. So now I take that Ravel and then I view it not as 64-bit integers, but as 8-bit integers. So now I have 12 by 8, which is 96 elements, one dimension, shape 96, and the type is uint8. And the strides, how do I get to the next element, is now 1 byte at a time. Okay? And if I look at those bytes, you learn a little bit about the architecture of your computer. This is called a little endian representation. So you see that the least significant digits are at the front of the number. So my number, which was 100 in uint64, is actually 100 in the first byte, and then 000 in the rest. So how do I demonstrate what that means? If I say a byte of 1, so I'm accessing this element, and I'm going to set it to 1. What this is going to do is it's going to add 256 to the value of a, because this number can go up to 255. This is the same as digits, right? You count digits up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then to get to 10, you actually put a 1 in the next location. So with bytes, you do the same thing. You count up to 255 in this byte, and then to get the next amount, you have to add 1 here. And now if I do a.ravel of 1, of 0, this is now this whole first element viewed as a 64-bit integer. I've added 256 to the value. Okay. Is anyone highly confused by this, or? I think it makes some sense. But the point is that of this whole exercise, you would rarely be messing with both bytes and 64-bit integers. But it's to show how the NumPy array relates to the memory in your computer. Okay, so let's take another example. If we do print information of A, we see that we have 12 elements, 2 dimensions. The shape is 3, 4. The data type is in 64. Strides are this. So we already went over this, right? Does everyone know what a transpose is? Can people raise their hand if they know what a transpose is? All right, most people. So transpose means you look at the rows and the columns backwards. So every row becomes a column, every column becomes a row. So if we look at a.t, which is the transpose in NumPy, we see that the shape is now 4 by 3 instead of 3 by 4. Everything else is the same, but the strides are 8 and 32. And the array is not C-contiguous, it is F-contiguous. So what this is showing is that a.t is not a new copy of the array. It's actually just looking at the exact same bytes, but in a different way. So by changing the strides, you can represent the transpose without copying any of the data. So again, this is something that NumPy gives you for free that you could not do if you were working with Python lists.
Sorry.
Yes?
Can it impact performance if you do operation between arrays?
can it impact performance if you do computations, operation between arrays that don't have the same C-contiguous or F-contiguous alignment?
Yes, but not always in the same way that you would predict. So, for example, if you're doing a matrix multiplication, the optimal order is for the left array to be C-contiguous and the right array to be F-contiguous. So, yeah, the question is quite deep. So I mentioned that when your computer fetches a value from memory, it doesn't fetch just that value. It fetches that value and a whole bunch of values adjacent to it, because it's predicting that if you want that value, you will probably want the next few values as well. So when your processing operation matches the order of the elements in memory, then your computer can go really, really fast. When it doesn't match that, then it will fetch a value, do a computation, look at the next value, see whether it has already fetched it. It will say, no, I haven't fetched it because it's in a different location, and have to go fetch it again. So that will be a lot slower. So this is memory efficient. Doing the analysis of whether your code is the most performant in terms of the memory ordering is quite hard. It's not always a matter of. So I think for 95% of use cases, you shouldn't really worry about your memory ordering. And when you're really trying to squeeze that last bit of performance, then yes, you should worry about it. I actually have a good example where I got about 10x performance increase by optimizing that ordering, but it's a bit complicated for here. Actually, I'm going to talk about it at SciPy US if you want to look out for that talk. But thanks for the question. That's exactly right. Any other questions? Okay. So I'll show you some other ways that NumPy does what it does with strides instead of copying your data. So we've already seen a.t, which gives you something. What happens if we skip rows? So this is called slicing. So this is giving me every second row of a.t. And you can see that what it does is it increases the stride in one location from 8 to 16. So in order to get to the next element, I'm not going to skip 8 bytes. 8 bytes. I'm going to skip 16 bytes. So that means that looking at the same memory, I can I'll come here actually. So if I want to get an array that instead of doing this, does this, then all I need to do is change the strides to 16 bytes. And then that will take me to the next element. And nothing else needs to change. I now have a 2 by 3 array instead of a 4 by 3 array, just by changing the strides and the shape. Okay, and the nice thing is that NumPy does this all behind the scenes for you, so you don't have to. And you'll notice that now the array is neither C-contiguous nor F-contiguous, because there's no axis along which your elements are one after the other. And so, any guesses as to what this will produce? Shape and strides? Feel free to shout out. Okay, so we already know that if we skip every other row, we get strides of 16. If we skip every other column, there's only 3 columns, so that means that you will be left with the first and the third column. So that gives you shape 2. And you know that you will have to skip twice as many bytes to get to the next location, so this will be 64. Okay. Another consequence of this whole model is that you want to be sure, you want to keep straight whether you're looking at a view of your data or whether you're looking at a copy of your data. Because if you have a view, I already showed here, a bytes is a different Python object to a, but if I modify a bytes, I also modify a. So you want to make sure that you understand when you have a view and when you have a copy. So I'll demonstrate that here. If I say b equals a, well, that's obviously a view. That's actually trivially a view, so this is our a. And if I modify a of 0, 0, then I also modify b at the same location. So in order to get a copy that is independent, that we can modify independently, what you would want to do is say c equals a dot copy. And now if I do, by the way, I will also make this completed notebook available to you, so don't feel like you have to keep up with all of my typing. So now if I do a of 0, 0 equals 5, print c, a of 0, 0 equals 100, I'm just restoring the original value. We see that c has not been changed by modifying a. Okay, so every time that you want to make an independent array that you want to modify without modifying the original, use dot copy on the array. This is a source of many, many bugs in Python. Okay. So we've seen one way in which NumPy arrays are more appropriate than Python lists for when you have homogeneous data, a rectangular grid of the same type of data. So it's more memory efficient, but it also gives you an easier way to process your data. So let's have a look at some of those things. So we were working with this tiny example of expression data. Now we're going to load a real example. This is actual data from the Genome Cancer Atlas. So there are 20,000 genes. So every gene in the human genome has been measured, and 375 patients. And these are samples from skin cancer. So these are gene expression counts, just like we discussed earlier. And there's this many elements, 2 dimensions, as I mentioned. There are genes along the rows, patients along the columns. The data type is 32-bit unsigned integers. So the strides are now 4 bytes along the column. Yeah, so it's actually an F-contiguous data set. I find that surprising. Must have to do with how I processed the data beforehand. And then to get to the next patient, you need this many steps. So let me draw that out just to clarify what we're talking about. So again, you have a rectangular array. It is 20,000 genes and 375 patients. It is Fortran ordered, which means that this is the order in which the elements are stored. And so to get to the next row, you need 4 bytes. To get to the next column, you need 4 times 20,000 bytes to get to the next column. And so this is all one big linear piece of memory, and this is how the array, NumPy views that array. Okay. So again, I mentioned one of the things that we're going to do is we're going to divide by the total number of reads in each sample. So for each of the 375 samples, we want to take the sum along that column, and that's the total number of reads, and then we will normalize by that sum. So this is the library size, and I can show you that this is a 375 element array. Okay, so this is something that NumPy gives you very easily. If you want to take the sum of a whole array, so total equals np.sum of x_, this will take the sum of every element of the array. But if you pass it an axis argument, this will take the sum over the 0th axis, which is the rows. Okay, so now we're taking the sum along all of those, of all the rows, and you end up with an array that is here 375, and this is called libsize. I'll just draw now so that I don't have to come down. Later we will load an array, so this you can't get from the data, you need a separate piece of data. That will be 20,000, and this will be the gene size. Remember that we want to divide by the gene size because we want the total number of molecules, we don't want the number of reads, and the number of reads is proportional to the number of, to the size of the molecule. Okay, so we're going to do our first exercise. This exercise will use the functions, the axis argument of some of these functions. Oh, I committed the answer. Let's erase that. You guys do the same in your, please erase the answer from the, and then try to come up with it. Okay, so we'll take 5 minutes for this exercise, for the two exercises. Maybe 10 minutes. So if you have any issues with it, please raise your hand. And then, yeah, we'll go over the answers together. So let me read out the first exercise. So you want to generate an array that is shaped 10-3 of random numbers, and I've already shown you how to do that. Now, from every row, you want to find the column that contains the number closest to 0.75. And you can use these functions that NumPy provides, abs, which is the absolute value, and argmin, which gives you the position of the minimum along an array. Okay. And once you're done with that, you can do the second exercise, which uses the full data set. You want to find the variance using numpy.var. And then you can use argsort to find the highest variance. And then you can index the matrix to get a matrix which only contains the most variable rows. Okay, and I'll be walking around and helping you out, so just raise your hand if you have issues. Okay, I'm going to go over the answer to the first exercise, and then I'll read over the second one and give you a bit more time to finish it, because I think the first exercise will help you to solve the second one. So the question is, we have 10 random numbers, And from every row, we want the column that contains the number closest to 0.5. So this gives me the numbers, and I'm going to show what that looks like. So now we want to find what is the index of the column that has the closest element to 0.75. So here, for example, we want the index of this number because that's the closest to 0.75 of these three. So this would be 1. Here you would have 0, and so forth, because these are further away from 0.75 than this one. So the first thing that you want to find out is the distance from every number in the column, in the matrix, to 0.75. And so dist 75 is equal to, so this is where we use the absolute value. Okay, and let me just print that. So now you want to find the location of the smallest number here. And I'll show you a Jupyter trick. This works in both IPython and Jupyter. You can say np.argmin ? And then if you execute that, you will see the documentation for that function. Okay, so it just pops out here in the bottom. So you can say it returns the indices of the minimum values along an axis. So this is where you can use the axis keyword to say, I want the minimum along the columns. So you say axis equals 1. So again, if I do np dot, by default, yes. So if I do, let me just not change this. If I do np.argmin of dist 75, it gives me the location, again, in the raveled array, so the full linear array of the smallest value. So the 18th value would be something on the 6th row, so this is it. Okay, so it's found, this is 0 to 2, this is 3 to 5, and so on. So it's found the smallest at 18. But now if I say axis equals 1, it gives me, this is the smallest value, then this one, then 2 over here, then 0 again, 0 again, 0 again, 1, 1, and 2. Okay? So that's how you use the axis keyword argument. In many NumPy functions, almost all of them, you can do the processing along an axis using this axis keyword argument. So can I see a show of hands? How many people have done the second exercise? Couple. Okay, so I'm going to repeat the exercise and then give you guys another 5 minutes to do it. So the idea is that in many cases, like when you want to do clustering of the samples, the computation is expensive and you don't want to use a 20,000 element matrix because it would just take too long. And you actually only want to keep the rows that are most informative for some measure of information. And one very simple measure is the variance. So how variable is the row? If a row of data is completely flat, then that row does not give you any information about the differences in the samples, so you can just throw it out. So by extension, if a row is highly variable, then it might give you some information about why the samples are different. So we want to keep only the 1,500 most variable rows. So you should use np.var to find the variance along a row, and then use argsort to find the values of the smallest, of the highest variance. And again, use the trick with the question mark to find the documentation for these functions. And then use these as an index to get a smaller matrix, which is now 1500 by 375. Okay, so we'll take 5 minutes and do that. Okay. I'll go over the answer now. The other thing I want to reiterate, these exercises are a lot more fun and easier to work with if you pair up and discuss them together. So I really want to encourage you to shuffle. Maybe we're having a break at 10:30. Maybe after the break, people can pair up. Because the exercises are only going to get harder. Okay, so again, to find the variance, you can use np.var, and you can look at question mark to get the documentation, and you see that np.var also takes an access argument. So in order to find the most variable rows, we can say most variable rows equals np.var. No, sorry. Row variance is np.var of expr. Axis equals 1, so we want to find the variance along the columns. And this should give us one value of variance per row. Now, in order to find the most variable ones, the location of them, you can use np.argsort. So again, let's look at the documentation. So you can see that, so in this case, we're going to sort this one-dimensional array, so we don't need the axis, but it's going to give you an array of indices of the same shape as A that index the data, so that if you index the data, you get the results in sorted order, so smallest to biggest. So now if I do row variance order equals np.argsort of row variance, should give me the order. And now I said argsort returns the values from smallest to biggest, and we actually want the biggest ones. So now we can say most variable rows is equal to row variance order of minus 1500 to the end. Has everyone seen negative indexing in Python? Yeah, so to get the last element in Python, you do -1. To get the second last, you do -2. So here to do the 1500, you do -1500 colon, and that implies to the end. Okay, and now I can say most variable data is equal to expr of most variable rows. Now most variable data, I think, yes, has the right shape that we were looking for. So these now contain the 1500 rows that are the most variable across all the patients. Let me just show that. Close this. Okay. Any questions about that procedure? Okay, so the next thing that we're going to talk about is this. Oh, yes, sorry. Yes, go
すいません、日本語でお願いします。
ahead. Yes.
ソートの時にオーダーをつけずにマイナス1500ってやってるんですけど、マイナス1500コロンってやってるんですけど、このオーダーをつけるのとマイナス1500コロンってやるのはどっちが、まあこうやるしかないのか、 マイナス、オーダーをつけた方がいいのかっていう問題と、もう一つあって、ソートアーグソートをインデックスして1500件にしてると思うんですけど、最後に1500件をピックアップするっていう2つの方法があると思うんですけど、これはこの方がメモリ効率がいいということでこっちにしてるとかってなんか理由があったら教えてほしいんですけれども。
So I'm not exactly sure what alternate way you would do. So let me try to explain the steps a bit differently. So in order to, if you do argsort, you get the indices that will sort the data. Now the thing is that your row variance is has this shape 2500, but expr dot shape is 2500 375. So if you only do, for example, sorted row variance equals np dot sort row variance, there is no way for you to know how to use these variances to sort the full matrix, the full data set. So let me just show you what that looks like. So if I do, let me show you a bit of plotting in Jupyter. So I could do import matplotlib.pyplot as plt, lt.plot. Actually, I should do that here. Oh, no, that doesn't work. Okay, so this actually puts the plots into the thing. So now if I do plt.plot row variance, so this is the variance of every row of the 2500. And if I do plt.plot of sorted rows variance, you see that these values have now been sorted in, sorry that it's a bit big. So these are all those same values. So you can see all of the flat bits are at the front, and towards the end you have the highly variable genes going up. Now, in order for me to find what grouping, so how these little spikes have been moved to the end, you have to use argsort to get those indices. So that's what tells you, the indices tells you which row ends up at that final position. Okay. So once you do that, then you can get you can use that to move the expression values, the full rows of the matrix, and get the last view. Does that answer your question more or less? Okay, thank you. Anything else? Any other questions about this? Okay, great. Okay, so I mentioned early on that we were going to divide the whole, every column by the library size and every row by the gene length. So this is what is called broadcasting in NumPy. So the reason it's called broadcasting is because you take this small value and in a sense you broadcast it over the whole array. So now you take one row and you sort of expand it into many, many rows. So that's the basic concept. And I'll talk a bit about how to use it. Okay. So the simplest version, and I think many of you will have already seen this, is that in NumPy you can broadcast single scalars, so single values, to a full array. So as a reminder, A is our tiny matrix. And if I do A plus 5, then this 5 will be added to every single value in that matrix. Okay? Now, if I want to add a row, so now we're adding 1 to the first column, 2 to the second column, 3 to the third column, and 4 to the final column. Then that also works. Okay? And the reason it works is that the shapes are compatible, and I will tell you exactly what that means. But in this case, it's just kind of works like magic. So you have an array that is 3 by 4, and you have an array that is 4, and it will divide. It will do mathematical operations automatically for you. And this is all done in a low-level C library, so it's very fast, very efficient. Okay, but if you try to do it with this, that's not going to work. So it says the operands is the two arrays on either side of the plus sign, could not be broadcast together with these shapes, 3, 4, and 3. So there's a 3 there, and you wonder why can't it match them? And the reason is that the broadcasting rules have to be general. So if you have a 3 by 3 array and you give it a length 3 array, it needs to know, is this going to be the rows or the columns? So now if we do this way, it works. Now you see that you've got 1, 2, and 3. Gets added to the row 1, 2, and 3. So let me explain what this compatibility means. So the way that NumPy aligns arrays for broadcasting is that it does it right aligns the data. So if you have 3, 4, and you have 4, then this works. And the reason it works is that NumPy implicitly puts a 1 to the left of this. So when you give it an array of just shape 3, then NumPy says, okay, this array has 1 dimension, this array has 2 dimensions, so I'm going to prepend a 1. And now you can see that these, the 3 and the 1 match. So if you have something that's just 1, it can be broadcast along that dimension. Or if you have something that exactly matches the shape, then that can also be broadcast. But if you have a 3 and a 4, then NumPy doesn't know what to do anymore. So what you need to do is you need to manually make this 3, 1. And then now you see that the 3 and the 3 matches, and the 4 and the 1 match. And now you can do the broadcasting along this dimension. Okay, any questions about these broadcasting rules? Okay, good. So now in this case I've made, I'll show you, if you look at b.shape, I've made this 3 by 1 array, and so now the broadcasting works. So this is a 3 row 1 column array by using this notation. Okay. So now we're going to look at the shapes of the lib size, which I mentioned is the sum. Actually, I'll just recompute it so that it's here. So this is the sum along all of the rows of the expression data, and you get the library size. So now if I print the shapes, you get this. Our full expression data is 20,000 genes by 375 patients. The library size is 375 patients, so there's one library size per patient. And if I do this thing with NumPy.new axis, this inserts a singleton axis, or an axis of size 1 in front of the array. So this is saying, give me the library size with a new axis and then all the data. And now you have 1 and 375. Now, are these two shapes compatible here? Anyone want to answer that? I mentioned the way that you check is you right align the data. So, so this 375 actually goes all the way to the right. And so you see that 375 and 375 matches, and then the 20,500 has an implicit 1, just like the 4 and the 1 in the smaller example. So in this case, dividing this by this will be the same as dividing this by this. NumPy is actually doing this implicitly in the background for you. So you can check this with numpy.all. So I'll mention what numpy.all does. So np.all checks that everything in an array is true. So true, true, false. That's false, but if I do np.all of true, 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 then it's true. Okay, so now I say, does dividing xper by lib size equal dividing xper by lib size of new axis colon, which is this reshaped library size? And the answer is yes. It's exactly the same thing. Okay. So now we're just going to do it. So the expression normalized by the library size is just xper divided by lib size. What happens when you do this, you get some very small numbers because every value is much smaller than, you have 20,000 things that you're adding together, so dividing by the total gives you some very small things. So you notice that it was reads per kilobase per million reads, so you multiply by 1 million to get that per million reads. Okay? So that's just a scale factor. You don't have to worry about that. Okay. So now I mentioned that there is a column of gene size. It's in that diagram there. And that data is not, you can't get it from the expression itself. You have to load separately. So you have this data set, genelengths.npy, and it has the shape 20,500. Okay, so now you're going to use broadcasting as an exercise to normalize the expression, normalized by number of reads, and also normalize it by the gene length. So a priori, I'm sorry, I committed just erase this. I apologize for committing the exercise solutions. They're not all there. So yeah, please erase that. So now you want to find the expression to divide the expression by the gene size. And keep in mind those broadcasting rules that I talked about before. Okay. So we'll take 5 minutes, then I'll go over the solution, and then we have a coffee break. Okay. I'm going to quickly go over the solution because we're coming up on break time. So I mentioned that shapes should match in the sense that they should either have the same number of elements, or they should have, or one of them should be 1. So in our case, we have a 20,500 by 375 two-dimensional array, and then we have a 20,500 number of gene lengths array. And remember that the shape should be right aligned. So if you right align this, then you have these two things matched to each other. And obviously that's just not going to work. So in order to do the broadcasting, you actually need an array of shape 20,500, 1. Okay, then the 1 can mesh to the 375 and broadcast along this dimension, and the 20,500 can match the 20,500. So let's see how we do that in NumPy. Okay, so this is the formula. Note that we have already done the divided by n and divided by 10 to the minus 6. So we just need the L and the 10 to the 3. So now if we look at gene len.shape is 20,500. In order to get a one-axis, I mentioned this earlier, right? So I do gene len of colon np dot new axis. So this puts an axis at the end of the array. And now I can do dot shape. And this is my 20,501 array that is now compatible with expr dot shape. Okay, you can see that these two things can be broadcast together. And this is really important to understand because in many cases like here, if you do the wrong thing, then the shape mismatch will cause an error and you'll be like, oh, okay, I need to fix that. But there's many situations where you will have more than one dimension that is compatible, and you really need to make sure that you are dividing by the correct dimension and doing the broadcasting that you think you're doing. Okay, so now in order to do RPKM, remember that we've already divided here and multiplied by 10 to the 6 here. So now we just need to divide by this reshaped. So expr lib divided by gene len colon v new axis. So actually, let me just show you what happens if you do it incorrectly. And then we're going to multiply by 1,000 because it's per kilobase. That's the K. And so you see again, operands cannot be broadcast together with these shapes. Because again, NumPy, whenever the shape is not complete, it will put a 1 in front, not in the back. So you want to do gene len of colon np dot new axis. And now that should work. RPKM dot shape is the is the same shape as the thing, but now it's been normalized by the two values. So don't worry about this code. It's just doing a density estimation, which is a fancy histogram. So we're going to see that the normalization makes the data look similar. By the way, the second line here just makes the plots look sharper for modern displays. If you have a slightly older computer, you can remove this line and it'll draw a bit faster. Okay, So this is, first I'm going to show all 375 samples plotted together. And then we will see what happens when you do the normalization. Now, because of the way that gene expression varies, you usually take the logarithm of the values instead of the raw values, because otherwise, basically all of your values end up squished in one corner. So this is what they look like, and you see that there's one sample that had a much smaller library size, so much fewer, much smaller multiplier of the gene, of the RNA molecules into the molecules that are eventually measured. And once we do the normalization, you will see that these densities come quite a bit closer together. And this is what happens when you work with slightly larger data sets. Okay, so you see that single line is now part of the whole big. Actually, it's probably this one. Yeah, so this is just one way to normalize gene expression data. There's more sophisticated ways these days, but this is a good one to illustrate how to use NumPy for this kind of analysis. Okay, so now we're going to take a break until 11. There is coffee and refreshments in the sanctuary room that way. So we'll start again at 11. Okay, if everyone, if someone hasn't downloaded the notebooks yet, this is where to go: github.com/jni/SciPy Japan 2019. And that will be where my completed notebook ends up as well. Okay. Do people have any lingering questions about the broadcasting syntax that we did? Okay. So we're going to do a slightly going to go right into an exercise. So what I want you to do is to use broadcasting now to produce a bigger array than any of the first two arrays. So here we have X, which has size 3, 5, so 3 rows by 5 columns. And we have Y, which is just 8 values between 0 and 10. And we want to produce an array Z such that which has 3 dimensions, and the value ijk contains the sum of xi. Oh, that's not right. These should be turned around. I apologize for this. So this should be y, because y is one-dimensional. And x. And this should be x and y. Okay, so Zijk, it doesn't matter which order you do it in, but it should have yi added to x of jk or xij added to y of k. So use broadcasting to do this. And once you've done that, then use NumPy.broadcast arrays. So have a look at the documentation for that, and see how broadcast arrays produces some arrays that have the same shape as Z, but there's something strange about them. So use our printinfo function that we defined at the very start, to look at those two arrays. Okay, so we're going to take about 10 minutes to do this. And as always, please raise your hand if you have questions about what you're supposed to do or any of the functions that you're using, or if you see an error that you don't understand. I or some of the helpers will come and help you. And another reminder, please discuss with your neighbor if it makes it easier to figure these things out. Okay. Hope some of you got the answer or got far enough along to understand what we're aiming for. So I think when people stop to think about the result, most of you got that the result, the shape of Z should be a three-dimensional shape, and it would have values, axis lengths of 3, 5, and 8. Okay, in order to have this many entries, because it has the sum of yi, x, j, k. So in order to have that many entries, you need the product to be, the shape to be 3, 5, 8 or 8, 3, 5. Both are correct answers here. So now let me just write x dot shape is that, y dot shape is that. So again, if you just do x plus y, nothing is going to work, right? Because you need, you right align the shapes, and 5 and 8 don't match together. Even if you do, even if you add a 1 to the end of this, it also doesn't help, because then you have 5 and 1 which matches, but 8 and 3 don't match. So actually you want to add 2 new dimensions to y and then add them together. So I can do equals x plus y of colon np dot new axis. Okay, and then that works. So let me just show some alternatives here. So this gives me 8 by 3 by 5, and now the element z of ijk will contain, the first dimension is y, so the sum of yi and x of jk. Another way to do this would be z equals 2 x of colon np dot new axis. Plus y. Oh, no, it won't. Oh, sorry. So x has 2 dimensions, so I need to put 2 of these here, and that should work. Another thing that you can do in NumPy is dot dot dot, and now this means all of the axes before this get added. So that's what I was thinking of doing. Okay, so this dot 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 and this are equivalent, except that dot 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 will work even if x was 15-dimensional. Doesn't matter. So I tend to like that better. Okay. Any questions about how that works? So now if I do z dot shape, it's 3, 5, 8. So they're the 2 ways of doing it. If you want to be very explicit about it, you can do y of np dot new axis, np dot new axis, colon. Okay, so now you have a 3-dimensional array which has shape 3, 5, 1, and then this one has 1, 1, 8, and so you end up with 3, 5, 8. Now, the reason we didn't need to do these is that, as I mentioned before the break, doing NumPy implicitly puts new axes in the front of the array. Okay. Did anyone get to the second question? No? Okay. This one is fun. Okay, so let's look at the documentation of np.broadcast arrays. So before we start, I just want to make a point, which is that if we have x equals np dot, no, I don't want to override x, a equals np dot zeros 5, 5, b equals np dot ones 5, 5. So these are two arrays that have shape 5, 5. And we know that if we add them together, we get an array, we get an element-wise addition, so that every element of A is added to the corresponding element in B. So we know that NumPy very intuitively can operate on arrays that have the same shape. Broadcasting just generalizes that to compatible shapes. So now if we look at np.broadcast arrays, question mark. So this gives us the documentation. So what this function does, it says broadcast the number of arrays against each other. It gives you arrays that are that all have the same shape. So internally, this is what NumPy is doing to broadcasting. It's going to take this, for example, 1 by 1 by 8 array and broadcast it to make 3 by 5 copies, and you will get a 3 by 5 by 8 array. And then you can do the element-wise addition the same way that you would do the addition of A and B here. So let's have a look at how that works. If I do x broad, y broad equals np.broadcast arrays, and we want x, and here again we need to make sure that the shapes are compatible, so let's take that second version, so x of dot 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 np dot new axis y. Okay, so again these are the two things that we broadcast together. And now we can do print info of x broad. Okay. Can anyone point to something weird about this array? Yes? Go ahead. That's right. There's a 0 stride there. So what does that even mean? And if I do print info of y broad, you will see that the stride is 0, 0, 8. Okay. So I'm going to go and draw about this. So remember that y started out as a single row. Just a second. So let's say that y is this. I'm going to erase the previous thing. Okay, so y has 8 elements. Is that 8? Yes. This is y. Now we want to repeat y in such a way that it has shape 3, 5, 8. So here's 3, 5, and now 8 here. Okay. So, and each of these columns is y. So now, to get to the next element of y, because it's a 64-bit number, we need to go 8 across. Now, if you have an array of shape 3, 5, 8, like we have here, to get to the next element along the last dimension, you're moving along the original location of y in memory, so that's 8. But to get to the next point here, in terms of the memory that we have originally, you're just repeating the array, so that means that you can just stay in the same location and you get that value, right? So all of these values point to y of 0. And so if I want to move to the next point along this 3-dimensional array, in terms of the value in memory, I just stay in the same location. And this is the same at any point here. So if I'm here, sort of deep into the array, I'm over here, and I want to move along this axis, then I just stay along here and I get the value correctly. So in terms of the information in this 3 by 5 by 8 array, again, it's just the value of y repeated, and so the total information is contained in these 8 values. And all you need to do is you need to do a bit of magic in NumPy to make a virtual array that instead of taking up this whole amount of memory, only takes up 8 elements worth of memory, and then has some metadata that lets you see it as a 3 by 5 by 8 array. And this is the same of the X array, which is like this. And now you have the same, just your standard to go to the next row, it's 40. To go to the next column, it's 8. But to go backwards in the array along this axis, you just get another copy of X, and so you have a stride of 0. Okay, so let's try to do some exercises with this, and we'll see how powerful this can really become. Okay, and just as a reminder, this is what NumPy is doing when it's in the background. To convert the broadcasting problem into an element-wise multiplication problem, you just change the metadata around the arrays, and you get these arrays that have exactly the same shape, but they have different strides, and that means that you can do you can see these arrays as bigger arrays than they really are. Okay, so I want to show you what I think is the simplest way to manually do this yourself. And then you can see that there's other tricks that you can do. So if I want to repeat an array that is linear, and I just want to repeat it a number of times along the leading axis, then I take my original array, and then I prepend n, the number of repeats, to the shape, and then I just add a stride of 0. And by adding a stride of 0, we are now saying every array along this axis is the same as the previous one. Okay, so you can see that. Let me make this 2 steps. Okay, so now print row, print repeated row. Okay, so you see that we have an initial array of random numbers, and now we repeat that array 4 times. And we've done this by defining these 0 stride, but shape of n, in this case n is 4. Okay, and if I do print info of repeated row, it's what you would expect now, which is that the strides are 0 in the leading row, but the shape is 4, 5. Now, one of the things that you need to be really careful when you're doing these tricks is you can end up with an array that takes up a small amount of memory. So here, even though it's 4 by 5, we only have 5 elements in terms of the data that you're consuming. But if you do a copy of that array, then the whole full array size will be copied. So again, this could be, let me show you. I can do repeat row 10, 1 billion. I'm not going to print it now because that will be very big. But you will see that it happens instantly. So I'm not actually materializing 1 billion rows of data. I'm just virtually copying this thing. And if I were to do a copy here, then it will try to make an actual array that is 1 billion. Let me just print info repeated row here. So it will make a 5 billion element array. Again, here, because the strides are 0, there's actually only 5 elements in my array, and it just repeats it. To look at the next row, it just goes 0 times the number of rows and ends up at the same position as it started and gives me the same value. But if I do a copy, I'm going to go back to the small number. Then you can see that now the strides are normal, 8 and 32. And yeah, the shape is the same as it was before. And it is now Fortran contiguous for some reason. I'm not sure why, actually. Okay, so that's how strides work. And this is the very powerful use of understanding NumPy metadata. And we'll see some uses, some more interesting uses than repeat, although repeat is actually itself quite useful. Okay, so the first exercise, again, nice if you discuss with your neighbor, is to look at a different array, which is a 3 by 2 array of random numbers. And now I want you to, before you use printinfo, try to predict, just with pen and paper in your head, what the shape of the array is, what the strides of the array is, whether it is C contiguous, F contiguous, or neither. And this, when you're looking at the strides, remember that the data type is important. And then use repeat of x4, and then figure out what the shape, strides, and whether it's contiguous. So again, do this in your head before trying printinfo and looking at the answers. And once you're done with that, then I wanted to use as strided, so refer back to my implementation of repeat to do a different thing, which is a sliding window. So if I want to do a sliding window of this array has values 0, 1, 2, 3. So now at the first position of my sliding window, I want the values 0 and 1. So I want the first 2 values. Then at the second position, I want the next 2 values, but sliding 1 over. And then finally, the 2 values 2, 3. Okay, so this is an example that you can use to test whether your implementation is correct. Do people see what a sliding window is? I see some nods. Okay, so use the function stride tricks the same way that I was using it for repeat. Again, so you have a reference implementation. Where is it? Over here for repeat. So you just have to modify it in some way to get a sliding window. Okay, so let's do these 2 exercises. Take about 10 minutes. Okay. So I'll go over the answer now, unless someone wants an extra few minutes. Okay, so now if you have X and it's an array of numbers which has shape 3 rows and 2 columns, and it's of type float 32, so 32-bit means 4 bytes. The shape of X, you've given it in the input, is 3 by 2. The strides of X, for that you need to draw the array. So if you have a 3 by 2 array, so this is 3 by 2. Remember that each element is 4 bytes, and so to go to the and that by default NumPy uses C ordering, which means the rows go first. So this is the order of the elements in memory. So to go to the next element along in the next row, so along axis 0, you actually need to go 2 over. So 2 by 4 bytes is 8. And to go to the next element along the columns, then it's just 4 bytes, so it's 4. And again, I mentioned by default, this array is C-contiguous because that's just NumPy's convention. So if we do that, and we say y equals repeat of x4, now we can do, so now we need to do the shape of y. So we've repeated x 4 times. You remember that when we wrote repeat, it inserts the axis at the beginning. So now the shape of y is 4 by 3 by 2. And the strides, because y uses repeat, the first stride will be 0 because the element along that axis will be the same as the element in the previous plane, basically. So the strides will be 0, and it will be neither C-contiguous nor F-contiguous because any strides that are different from 0 that are different from what you would expect along the every dimension will make it not C-contiguous. So having the 0 stride means it's not contiguous in C format. So print info of x. That's what we expected. And print info of y gives us this new shape and new strides. So in general, when you're using stride tricks, you're going to end up with a non-contiguous array, and that's okay. Contiguity becomes very important when you're doing linear algebra because all of those libraries expect contiguous arrays. But when you're doing these kinds of NumPy operations, it matters a lot less. Okay, so sliding window. Can I get a show of hands if anyone got this? Approximately. A couple of people. Yeah, okay, good. So it starts to get challenging, but hopefully you will get what the answer is. So now you see that the values in the sliding window array are the same as the values in the original array. So we've got 0, 1, 1, 2, 2, 3. These are all just 0, 1, 2, 3. But they are arranged in a different shape. So let's figure out what the new shape is. So I've drawn a couple of examples here. So you can see that if you do a sliding window of size 2, and you have an input array of size 7, is it 7 down here? Yes. Then you end up with 6 sliding windows So there's window 0, 1, 2, 3, 4, 5. And if you do, so each of these is 2 elements, and they're just sliding by 1 element at a time. If you do a sliding window of size 3, then you end up with 5 windows. So it's 0, 1, 2, 3, 4. So the actual formula is for the shape that you get is the original length minus the size of the window plus 1. Okay, so here we have 7 minus 2 plus 1 gives us 6 windows. So that's the shape. And the next piece of the puzzle is the strides. And so when you look at the sliding window array, let me erase this one. If you look at a sliding window of shape 2, and again we have 6 sliding windows. So we have 0, 1, 1, 2, 2, 3, 3, 4, 5, and 5, 6. Okay, so these are all the elements in my original array. To get to the next element here, how many steps do I need to take? So it's just 1 step, right? So this is 1, and remember that strides are in bytes, not in number of elements. So this is actually 1 times the stride of the original array that you got in, right? So this is actually our dot strides of 0. Okay, and now to go down this way, how many steps do I need to take in the original data? No, so in the original data, remember the original data is 0, 1, and here it's 0, 1, so it's actually still just 1 step. So remember that our data looks like this. 0, 1, 2, 3, 4, 5, 6. So to get to this element, to have a 1 here, then I'm only stepping one element over. So that's the trick for the sliding windows, is you have the same stride in both the rows and the columns axes. So let's see what that looks like. So single stride is equal to, what's my input array? It's called R. So it's R dot strides of 0. And then I'm just going to call this stride because it's a bit smaller. Now the new shape, as I mentioned, so n windows is equal to R dot size minus the window size, minus size, plus 1. So size is the size of the window, as I wrote here. And so now we can say return np.lib.stridetricks.asstrided. You put in the input array, and then remember, so I go back to the example that you had for repeat. So you have to give the original array, the new shape, and the new strides. So now the new shape, where am I? The new shape is shape equals the number of windows and the step size, right? So the number of windows in terms of that's the number of rows, and the window size is the number of columns. And strides is stride, stride. So the same stride to go along the rows as to go along the columns. Okay, so I think this should work. And if we run this, then you get this sliding window. So every element in this array is a index of elements along the original array. So I hope you can see that using these stride tricks and knowing about the format, the data format of a NumPy array can help you to do some interesting things with your data set. So I'll try to move a bit quicker, given that we're going to run out of time soon. And I'm just going to demonstrate this one. But feel free to play with it at home as well. So what do you do once you have a sliding window? So a common thing to do is to do mean filtering. This is actually, you might have heard of convolutions. So this is the simplest convolution you can do. So you take a sliding window and you replace the value at that position with the mean of those values in your window. And that means that's a simple trick of signal processing to reduce the noise. So I'll show you what that looks like. So the nice thing is we can reuse our sliding window code. So we can say signal sliding is sliding window of signal and window size. And now what do we want to do? For every row of that matrix, we want to take the mean of those values. So now we can reuse the thing that we learned in the first half of the tutorial, which is that NumPy has axis-wise evaluations. So I can say signal filtered is equal to np.mean signal sliding axis equals 1. And we return the filtered value. Okay, so I kind of want to show two things here. The first one is that you can use this sliding window trick to do some real signal processing. And the second one is that you can compose these operations. So we're reusing the sliding window code here to do something a bit more sophisticated. And you can, in a sense, you take that complexity from the stride tricks, which is a bit of a mind puzzle, and you hide it away behind this function sliding window, which is a more intuitive way to think about your code. So let's give this as a test. So here I'm using, I don't really have time to explain in a lot of detail, but you can use a convolution with this difference filter, which has value 1, 0, and -1. So you multiply by these three values at every position in an array. And it is a change detector. So if you take three values along a window and there's no change within those three values, then 1 times whatever the value is, 0 times the value, and -1 times the value, when you sum those three things together, you will get 0, because the value at the end and the value at the start is different. But if there's any change in your signal, then you will get some non-zero value. And so this is what we're seeing here. You have a signal that has no change, no change, no change. Then it steps up, stays up, steps down, and stays down. And when you take the convolution of the signal and that difference filter, you get a 0 signal, a step, 0 signal, and a step. Okay? So the main problem with this kind of difference filter is that it's actually very sensitive to noise. So if your signal's a bit jittery, then this will amplify those jitters. So let me show you what that looks like here. So now if you have this noisy signal, for us, your brain is actually really good at filtering and noise reduction. So for us, it's quite obvious that the signal stops here, then it steps down. But if you do the difference filter, you can see that it's very jittery all over the place, and it's very hard to find the location where the signal changes. So what we can do is use our mean filter on this signal and then do the difference filter. So let's try ndia.convolve, yeah. So so filtered diff is equal to ndi.convolve. And now we want to use our mean filter that we did before. So here. Mean filter of signal noisy. Let's do a window size of, say, 5. And again, we used the difference filter before. And now we can do figx subplot plot filter diff. Okay, and now you can see that you have still a noisy signal, but the two transitions are well above and below the rest of the signal. Okay. So I'm going to skip the next line. I'll just give you a summary, which is that you noticed that when we did the sliding windows, the larger the window, the smaller the length of the signal, because you hit the edges of the array. So these are boundary effects. You can counteract those with a function called numpy.pad, and essentially you just want to add some extra data on the edges of your array before you do the filtering. So I'll be here all conference, so feel free to approach me if you have any ongoing questions about this notebook. So again, you have the whole notebook, and you can keep working on it, and give me a shout if you have questions. So I'm going to skip that bit. So I'm also going to do this. So I'll just demonstrate this rather than do it as an exercise, again, because we are running out of time. But the basic idea here is that the mean is actually a very crude way to filter your signal. And what you want to do in many cases is a thing called Gaussian filtering, where it's a weighted mean, where the value at the center is given a lot of weight, and the values around the center are given progressively less weight. So it's an average, but the average is smoothed so that the center always has the most value. So this is the weighting that you get. So it's a bell curve, which you might have seen before. So the first element the center element in your sliding window will have a filter, so it will have a weight of 0.20. The ones around it will have weights of 0.18, for example, and so on. So it drops off. So this will give you a much smoother reconstruction, and so I'll show how to do that. So now we have these weights. So let's look at weight.size. So it's 17. So how do we do this with the sliding window and the broadcasting and also our access-wise operations? So now we're putting together all of the stuff that we've learned this morning. So let me draw. So we have a sliding window of size 17. And we want to do, so here's our signal with the sliding window. So this is 17, and this is the length of the signal minus 17 plus 1. Again, using sliding window. Now we have a set of weights. That's here, which is your Gaussian shape. What we want to do is we want to multiply every row here. So that's every window gets multiplied by these weights. And then we want to take the sum along this axis, and we get your filtered signal. Okay, so this is, before we were just taking the mean of these values. Now we want to take the sum of the values times these weights. An equivalent thing for taking the mean would be to do this thing, but now the value here is flat, and it's 1 over 17. So you can see that if you take every element here, you divide it by 17, and then you add them together, then you get the mean. So now instead we are multiplying them by these Gaussian weights, and then adding them together. And that's the Gaussian filtered signal. So let's see what that looks like. So windows is equal to sliding window of signal noisy. Now we want to say Gaussian weighted is, well, let me just look at the shape. Print windows.shape, print weights.shape. Oh, is it wait. Oh, sorry, and sliding window should have size 17. Okay, so are these two shapes compatible for broadcasting? Yes, they are. Okay, so because you're right aligning them. Again, if you wanted to make it explicit, you could do weights of np.newAxis : but again, NumPy does this implicitly for you. It puts that one there. Okay, so now I can just do weighted is equal to windows times weights, and filtered Gaussian is np.sum weighted axis equals 1. So now we're summing over that axis. And now if it's weight, sorry, I keep messing that. Okay. And now if I do, let me look at my plot code here. So diff Gaussian is equal to ndi.convolve weighted filtered, diff, no, it's not weighted, it's filtered Gaussian. Okay, so let me just plot that. Okay, so you can see that the Gaussian filter gives us a very nicely smoothed signal out of the noisy signal. And now if we do the convolution, diff Gaussian. You get the two peaks, and you will see that it's quite a bit smoother than the mean filtered version. Okay, so this is why you want to use Gaussian filtering generally over mean filtering. Okay, any questions about all that? All right, so we're going to get to the last section, which is fancy indexing. Before I get here, I'm going to go back to the very beginning when we were looking at the differences. Some of you actually tried this and noticed that it wasn't working here, this exercise. So we have now, as a reminder, we have a 10 by 3 array of random values. And we find the column, the index of the column with the smallest, with the closest value to 0.75. Now you say, okay, what if I want to extract those values out, right? So I want to now get them. So I just say closest is equal to R of colon and let's just say indices. Okay, so we want call indices. Did anyone try this? Maybe not. Yeah. Did anyone notice the result was maybe not what you expected? Oh, let me. So you get some very strange thing that is 10 by 10 instead of just 10 elements. So the way to actually do this closest is np.arange. You basically, whenever you're doing indexing with NumPy arrays, the indices, and you have indices, so you can always do the slicing that we've seen in many places to do colon, colon 2 to get every second row and so on, or colon to get every row. But if you have indices, then now you're in fancy indexing mode. And now you have to pass in an index array for every dimension that you have in your array. So this array has 2 dimensions. And so we want to give, in the output array, we want to get the coordinates in the original array along 2 dimensions. So if I do np.arange r.shape of 0, and then, what did I call this? Call indices. Now I get my 10 values. So the reason is because I'm getting the, within array, I'm getting element 0, 1, okay? And so here in np.arange, sorry, for those that haven't seen np.arange, np.arange just gives you the consecutive values. So np.arange is that, and call indices is that. So now I want the element 0, 1 here, so that's this element. Then I want the element 1, 0, so that's 1, 0, this element, and it ends up here. Then I want the element 2, 0. So this is the first element, the first array that you give in to closest is the row indices, and the second array is the column indices. And now for every element in these 2 arrays, you get 1 element in the output. So let's take it back and look at some smaller examples than this one. But that's the basic principle. If you're indexing into a 3-dimensional array, then what you give it is a tuple of 3 arrays to index. If you're indexing into a 5-dimensional array, you give it a tuple of 5 arrays. Okay, so let's go to fancy indexing. Okay, here we go. So I'll give you a simpler example, which is the 1-dimensional example. And hopefully it will give you a better idea of how this indexing works. So we have an array of values, and the array has shape only 3. So it has the values 0, 55, and 9. And we have a selector, or an index array. And this selector has shape 3, 4. So it's here. And it has values between 0 and 2 inclusive. So each of these values can be a 1-dimensional index into this original array. Okay, so when I take my 3-element array of values, and I select this, then wherever there is this index 0, I take the 0th element of values. Wherever there is this index 1, then I take the first element of values, so you get a 5 here. And wherever there is an index 2, then I get the 3rd element here, and so I get a 9, 9 here. So you see the mapping between the linear indices and the values that you get out when you use values of selector. So it's actually a generalization of something that's very intuitive, right? If you do values of 0, 1, let's do 1, 2, 0. This makes sense, right? I think most people would agree that this is the thing that you would expect. You pass in a list of 3 indices, and you get the element at 1, the element at 2, and the element at 0. And you can repeat indices. Oops, sorry. And this element. So this is, I think, reasonably intuitive way to think about it. What NumPy does is it generalizes this to any shape of index array that you want here. So now, if I do 1, 1, 1. Oh, hang on. What just happened? Oh, I needed an extra. Oh, this is actually something that is an inconsistency in NumPy that they're about to fix, but they haven't yet fixed it. Sorry. So it needs to be an array. It can't just be a list. Okay, so before we had a 1-dimensional array of indices, which was 1, 2, 2, 2, 0, and you got this row of values. Now we have a 2-dimensional array of indices, and the output is a 2-dimensional array of values. Okay, I think that more or less. So the so this is 1-dimensional, and now if you wanted to do a 2-dimensional indexing, then that is what we saw before, where you have 2 or as many arrays in the indices, giving you the index along every dimension of every element. So here we have, this is the element at position 1 of the values array. Now if we do values 2 is equal to np.array, and I'm going to say 0, 5, 5, 9, 9. Sorry, let's make that simpler. So this is a 2-dimensional array. to say 8, 70, 80. So these are just values, right? Now, if I want to indexing to that, it's very simple to do values 2D of 1, 2. Okay, so I guess everyone expects that the value here will be 1, 0, 1, 2 will be 80. Yes? So now I can replace the row index and the column index by a list of row indices and a list of column indices. So I can do values 2D np dot array of 0, 1, and then 0, 2. Oh, sorry. Okay, so now instead of having a row index that's a single value and a column index that's a 0 value, I have a list of row indices and a list of column indices. So the output that we expect here is 2 elements, and they are the elements 0, 0, and 1, 2. And that's indeed what you get. Okay, so does that make sense how NumPy is generalizing a one-value indexing to a multi-value indexing, and this is called fancy indexing. Now, the interesting thing about fancy indexing is that it uses broadcasting. So if this array is just one value array, sorry, one element array, then it will be broadcast against this array so that you end up with the same shape array of indices, so that you end up with the equivalent thing to what we just did, which is the same number of row indices as column indices. And now NumPy can go and get all of the rows and columns. So if you broadcast this array of shape 1 with this array of shape 2, what ends up happening? You get, this value gets repeated, okay? So now you'll end up with the values 1, 1 for the row indices and 0, 2, so you will have 1, 0 and 1, 2. And so you should get 8 and 80. Okay, so this is the element 1, 0, and this is the element 1, 2. Hopefully that's clear enough that it doesn't look like magic. It took me a very long time for this to become intuitive, but you'll get there. Okay, so that's the basic rules of NumPy indexing. You have as many arrays of NumPy fancy indexing. You have as many arrays here as you would have indices in the single index case. So here we have 2 indices because it's a 2D array. Here we have 2 arrays because it's a 2D array. And so these are the row indices, column indices, and if you have 3D, then it expands that way. And the broadcasting can happen regardless of the type of the arrays. So that's what this section is doing. So let me explain what each of these steps is doing. So cell, split cell. Okay, so we have relabeled. So this is our array that we got earlier. So has large columns is a Boolean array. So if I do edit split cell, so this says if any of the values along the axis 1 is greater than 10, then put it true there. Otherwise, put a false. Okay, so now I have a length 3 array, which has the first row does have a value greater than 10. So that's true. The second one doesn't, so that's false. And the third one does, so that's true. Okay, so now this array is selecting only so this is Boolean indexing, which is also a part of fancy indexing. So it selects the columns that have value true. Sorry, the rows that have value true in this case. Okay. So now, yes, okay. So we're going to do a small exercise, and that will be the end of the tutorial, actually. But remember that you're doing fancy indexing, so you need to have your selector have the right shape in this case. Okay? So give me the columns of relabeled that don't contain the value 99. In the same way that here I took the rows that do contain the value 99. That's weird. Okay, so actually I don't think this exercise does what I think it does. I think you actually don't want to use Boolean indexing. You want to use fancy indexing, which means taking the non-zero values here. So the idea is you want to choose, if you choose has large columns and no 99, so there's no 99 here. Then with Boolean indexing, these get applied one after the other. And so you end up with a much smaller array. You actually want these two columns here, 5, 0, and 0, 5. So in order to get those, you want to do np.nonzero of has large calls. So you have an array. These are now your row indices. And so in order to be row indices, you want them to be you want them to be arranged in a column. So this would be n colon np. Oops, sorry. 0. Okay, so that's your two things. And now you want your column indices to be a row. So we just say np dot non-zero of no 99 0. Okay, and now if we broadcast these two things together, we get relabeled of has large cols. Oh, sorry, square brackets. That is not what I expected. Oh, sorry, I need to assign these. Did I not run this? Okay, and now we get the two things. So if you have a 2x1 and a 1x2 things broadcast together, you get a 2x2, and that's the output that you get. Okay. All right. So hopefully that makes some sense to some of you. Unfortunately, we don't have time to go into the quantile normalization, but this is in the book, Elegant SciPy, which, as I mentioned, is open source. Again, feel free to go look at the solutions online, do this on your own time, and send me feedback or my co-authors. So thank you. I think we're out of time, and see you guys at the conference. Any questions? Any final questions? No. All right. See you at the conference. Oh, yes. Sorry. Question.
話ありがとうございました。最初に
Oh, hang on,
の
hang on. I don't have my. Go ahead. Yes, yes.
ありがとうございました。最初にNumPyの配列からスライスとかストライドを行ってインフォメーションが変化することを見せてくれたと思うんですけれど、Python の内部ではどんなことが起きているんでしょうか。例えば新しいインスタンスができているんでしょうか。それともアトリビュートが変化しているんでしょうか。もう一つ質問があります。畳み込みの計算を見せてくれました。信号処理とか機械学習では重要な概念だと思うんですけれど、積和演算、その時に出てくる積和演算の、プロダクトサムオペレーションを軽くすることってできるんでしょうか。お願いします。
Lighter? Yeah, sorry, I don't understand what you mean by the lighter computation.
計算の量を減らすとか、計算の回数を少なくするとか、計算に時間がかかるのを短くする。
I see. So often I think, I'm sorry, I've forgotten your first question.
すいません。最初の質問がPython の配列からスライスをしたりストライドをするとインフォメーションが変わるのは Python 内部で何が起きてるんでしょうか。
Yes. So, I mean, this is a very broad question, but roughly speaking, when you're doing a NumPy multiplication, for example, of two arrays, Python is actually calling the NumPy library. The NumPy library is saying, okay, I have this array and I need to multiply it with this other array. And then because NumPy has information on the memory layout of those numbers, they can call C code. So it's code that's written in C. It tends to be very optimized for modern processor architectures, and that is the code that is actually multiplying these numbers together. And then a new array object does get created when you're doing these NumPy multiplication, addition operations. And that array object, it results in new memory with new numbers, the resulting numbers being put in that memory, and a new array being formed around that memory with all of that metadata that we talked about, the shape, the strides, and so forth. So that's how NumPy is doing it. In terms of is this the most efficient way of doing things, that's an extremely long answer. In many cases, yes. In some situations, NumPy is not the most efficient way. So I'll give one example, which is that if you have, let's say z equals x plus y plus q. So if you have these three arrays, let's add another thing, squared. If you have all of these operations one after the other, because of a limitation of Python, this operation will happen first. So that's normal in mathematics, right? And so what will happen is that you get one big new array of the same shape as Q containing the result of this operation. Then this operation will happen. And now you will get, this operation will happen. You will get an array, a big array that is all of those two things together. And then finally, the next operation will happen, and you will get a final array, which will be assigned to this value z. So this is a case where NumPy can be inefficient when you have many arithmetic operations in one line. There's libraries and new technologies within Python that are being used to minimize this. But in those cases, there's a library called NumExpr, which stands for numerical expressions, that tries to avoid this problem, because what you really want to do here, right, is to allocate the memory for your resulting array as z, and then you want to, for every element in z, compute this value. So then you don't have so much temporary arrays created. But I think in most cases, this doesn't matter that much, and it's better for you to focus on your code and getting your algorithm correct. And then at some point, when you really need to optimize, then you can switch to tools like NumExpr. In NumPy, you can also do a lot of optimizations as well. Because I think the Python language and the NumPy libraries themselves are evolving, and they're getting better and more efficient every day. So it's not a good use of your time to optimize all of your code to get rid of these inefficiencies. People are working to get rid of them for you. Thanks for the question.
ありがとうございました。
Okay. Thank you, everyone.